Thanks for staying around after lunch. Hopefully you'll find this interesting. We're going to touch on some subjects that people have started to talk about, which is dropout and loading, rather than having empty ship. And basically what I'm going to talk about is issues regarding tanker stability. This isn't problems with the regulations themselves, it's problems with the application and sort of advice of those regulations to the operators of the vessels, i.e. the master and mate. Again, this is a joint paper by Andrew and I on a piece of work we've been looking on. I think we gave a paper in Athens in 2011, I think was the first we did on this. So we've been bleating on about this for quite a while. And they are our opinions. So, I mean, they are good opinions, but in case there's anything, I think they're right, but certainly not part of Safinah or definitely UK flag. Okay, what I'm going to talk about, because it's straight after lunch, I thought I'd give lots of pictures. So I'll take you through some tankers so you can all sit and look at, oh, that was a nice ship, or that was horrible. Quickly take you through what the current damage stability regs are, and then issues with verification of those regulations. Then I'm going to move on to how do you establish a tanker is safe in a case of damage, and some recent developments regarding onboard stability information, developments over the last few years, and some guidance that's been given by UK flag. Okay, some typical tankers. There's a little bit of a bent here. The first one that notices what the bent is, you get a free macaroon if Philzilla hasn't eaten them all. This is a small little tanker. So we're talking about tankers from this sort of size, which is a 3,000 tonner, up to a 20,000 tonner tanker. Oh, look where it was built. Never mind. Next one. This is what we call a sort of medium MD Panamax tanker. It's quite an old one. This is mid-60s, even before I appeared on the scene. 70,000 tonner. This is basically an Aframax, 120,000, 130,000 tonner. This is a very famous ship from a certain place in the universe, built by a certain shipbuilder. It is called the BP Achiever, but locally it was known as the Banana Boat. But if you want to speak about that, we can talk about it later. He has a Suezmax tanker again, 164, 165,000, so up to nearly 272, 300 meters here. And he has a VLCC. It doesn't look very good, but I think it's a very atmospheric photograph. This is one of the ones that was built by a certain shipyard again, on a certain river. And it's actually going out the river on sea trials. And I think it's a beautifully evocative photograph, which is just entering into the harbour. And these are what are called the Black Middens. So if it hit that, it would be a damaged ship, but luckily it never did. It actually lasted 10 years, which for those VLs was quite a while. They had issues. And then we come up to the absolute Leviathans. And this is a ULCC, 450,000 tonner. 380 meters long, commonly known as the White Elephant class, as the White. They were built by DSME about nearly 20 years ago now. I think they all still exist. I think one's still trading, the other ones are all FSOs. But against that, just to give some idea of scale, is basically a 100,000 tonner against that. So that's on a small boat. That's 250 meters long. Yeah. So, yeah. The heat. Well, that's it. Pretty difficult to keep clean. Anchor chains and that. Also covers ships such as this. This is a UK auxiliary supply tanker. It's a combined EOR, diesel, fuel oil plus stores. And this was a ship I actually worked on. And just to show me age now, it's now dead. It got broken up, but never mind. And then it covers not just pure oil tankers, but also chemical tankers. And this is a large chemical tanker. Also gas carriers. So he has an LPG carrier. Theme, nobody said anything yet. Nobody's going to get the macaroon. but never mind. This is a one that was built actually from in the town I come from and still live in. In the mid-70s in Gandara, and she lasted quite a long time actually, didn't get broken up until then. So there you've got quite a small by modern standards, and this is a more common size, what's called a VL PG, a very large petroleum carrier, and these were about 75 to 80,000 cubic meters now. So quite big ships, 250 meters long maybe, and just to say that even though nothing's built on the Tyne, things are still designed on the Tyne. This is an 85,000 cubic meter that I designed a few years ago. And then we've got into not just petroleum gas, but methane, liquefied methane, a Moss type boat, 4-baller, about typically the range between 140 and some up to 180,000 tonners. More common membrane ships, typically around 180,000 tons, going up a little bit higher towards the 200 now. And, oh, there's the one I designed as well, so it's still happening a little bit earlier. And then into the monsters of the LNG fleet, which are the Q-Flex first motorboats from Qatar, which are about 215,000 cubic meters. Notice the length, 315, and then you've got the Q-Max, Leviathans of, the 265,000 cubic meters. But note the length has now gone up. These are the oddball ships. The drafts are still 12 meters, but the lengths have gone up. So about 300 meters is the length usually for an LNG. Just as illustrative purposes, I'm going to use this as a standard double-hull tanker. It isn't totally standard in that you'll notice that the wings are actually straddled to the tanks, but there are a lot of tanks, so it's more of a products carrier than a standard oil carrier, which you tend to see the big ones. Smallish, normal size ones are about 2 abreast. Big tankers are 3 abreast, and you've probably got 5, maybe 6 sets of cargo tanks. So we've got more on here. This is more of a products carrier. And that shows its disposition of fluids, equivalent to a capacity plan, cargo in the middle, ballast around the outside, fuel and fresh water. So you'll see this coming up all the time. So there's different regulations for different types of tankers. Oil tankers are governed by MARPOL, chemical carriers by the IMO IBC code, LNG carriers and LPG carriers by the IGC code. Basically, the damage is actually nearly exactly the same, roundabout figures with them. One funny one is FPSOs, in that they're not directly governed by MARPOL. They were a flat stake decision, but usually they call it MARPOL. But sometimes they call it module code, and we can talk about module code later on in the application to long, slender monohulls. Interesting try to justify that, in my opinion. And we also, as I've been discussing with some colleagues, tankers above 150 meters also have to comply with the old 1966 load line regulations, which recently changed in 2013. Another question. I've never actually seen this produced as a curve. So Andrew and I came up with this a couple of years ago to try to show it, because you see intact stability curves all the time, but you never see the damage curve. This is actually your MARPOL damage with your requirement for area under the curve, the GZ max, your equilibrium angle, and the range of stability. I like pictures, as you'll notice. We've got lots of pictures in here. So, what is MARPOL damage? So, this morning Andrew was talking about passenger ships, and we was talking about probabilistic and deterministic. Is everybody comfortable with that? What that is? Is anybody not comfortable? Everybody knows what it is. Well, you're going to find out what this one is. So this is, on MARPOL, that was like old SOLAS, you damage into B over 5. So you go, that's the maximum damage you can do. Probabilistic, you go all the way to the centre line. So you could damage the wing, you could damage a cargo tank. You can also get bottom damage on tankers. You don't get that on passenger ships. And obviously you can damage one side or the other, and also you get raking damage, which is a longer damage than a bottom damage. And just to illustrate what the side damage, that's one compartment damage outboard. You go through the longitudinal wall, the little damage is there in black. Goes through the longitudinal wall into the cargo tank, 2 compartment damage, so you're damaging 2, the transverse bulkhead in the wings, and then you can damage 2 cargo tanks as well. And that's the maximum extent of damage you can have, and it's vertical without limit. You can see an example here of what happens. I've tried to show a bit of trim towards the fore and aft end. And just to share with you, most tank has damage in the way of the engine rooms is the key. So we were talking earlier on about how quick you can do damage stability calculations now. In the old days, when it took to do a tanker damage stability calculation 3 days, so you set it off on a Friday, hoped it was finished on Monday, but probably was a Tuesday. You just used to concentrate on the back end. So what are the issues? The issues have been known for quite a long time. First came up by a survey by the MCA about 15 years ago, in that a lot of tankers were only looking at being compliant with intact regs, not with the damage. There was also found to be minimal margins on stability, and this is still happening even now with cases I'm looking at. Is some cases actually omitted by the shipyards, are just not looked at, which, given the fact that computation is quite cheap now, shouldn't be the case. Wasn't really any effects given to how the vessels are operated. I mean, shipbuilders are not ship operators, so you've got to understand that. I was a shipbuilder, then a consultant, but I'm not a ship operator. So the use of how the vessel's going to be used, if it's not defined to the ship owner, you can certainly get some of the issues maybe not addressed properly. And some approvals were based on what are classed as unrealistic operational scenarios. And at the time, okay, it's a small sample of level vessels, but 2/3 were found to be omit some of the critical elements for verification. So there were some major issues. The survey, the results were, well, can I say, quite frightening actually, for what is actually quite a safe industry. We don't have issues. Obviously, to have a damage, you have to hit something, or something hit you. But obviously, if it happens, some of these ships would have been in trouble. I'm not going to go through all the percentages and that, but you can see there were some major glaring issues there. In 2009, the MCA carried out another gathering exercise, which is detailed in the paper. And again, some of the issues were not substantial. About a third of the ships were loaded differently to what was approved in the trim and stability books. Now, as I'm going to illustrate later on, something which, and again personal, I think is nearly criminal, is that in a tanker stability book, traditionally you only put the intact curve. And in deep drafts, intact stability is not dominant, it's damage. So quite often a master had no idea that he was maybe sailing out with the thing, and what use out with the stability arrangements of the ship. And how you proved stability was direct calculation on the intact conditions in the book. So if you weren't within the conditions of that book, you couldn't actually verify you were safe. And anyway, these were submitted to IMO. A year later, the Paris MOU did an next inspection campaign, and all this is detailed in the paper as well. But also, it found quite a lot of issues, and not just from the fact that the master couldn't understand it, he couldn't actually demonstrate it was there, and in some cases, he couldn't actually read. Some of the crew couldn't read this trim and stability book, which, if you think about it, is the fundamental safety vessel document on board the vessel. It's how to operate the vessel safely. And you know, it was known for a long time issues with loading of tankers. That's why you have, or bulkers, that's why you had loading instruments. They were there purely for longy strength, not particularly for stability. Stability's always been a bit of a poor sister. That was also repeated then in the Black Sea. With quite a large inspection, nearly 250. And the outcut of those, you know, in some cases the master couldn't understand the book again, and in 88%, 41% had deficiencies. You know, this is on quite new tonnage as well. So this was found to be a major issue, and it did affect some of the regulations. What is the problem with tankers? Tankers, there's loads of them around. It's not difficult. The problem is you have this thing called dropout. So if you have a passenger ship, basically you don't have dropout. But tankers are deadweight carriers, even gas carriers or sort of semi-deadweight carriers. You have to allow that cargo, you can't flood a space that's full of something else. So you have to allow for that to be dropped out. Especially for products carriers, you can have various fill levels. Normal tankers either, sail from the Gulf to Rotterdam full, save back and ballast, just back and forth, back and forth, back and forth. Product carriers or tramp carriers are something different. And this belief that compliance by the operators from the port state inspections that intact curves were good enough was absolutely terrible. And you can see some of the lack of awareness of the complexity of dam stability calculations. Even some naval architects don't understand how complex it can be, which I'm going to show you in a minute. So this is bare boat. So if you imagine this was what Andrew was talking about earlier. If we damage that, it goes like that. If we're damaging further, it goes like that. Simple. No problem at all. However, when you put cargo in it, it's not always the case. So with damage in there, yeah, it goes in there, but then it plops the other way as the cargo drains out, because we're assuming vertical without limit, and the flood water is less than the cargo. Again, that would change if you had a half fill to a tank where it would actually go the way to what the damage is. In ballast, when you've got it at the water line, obviously it stays nearly exactly the same, but then you damage into an empty cargo tank, bang, over she goes. Again, with a low SG cargo, fully flooded, fully filled, yes, she'll go over, and then you penetrate inboard. She probably goes back over because the cargo is less dense, significantly less dense than the flood water. That would be the case of a gas carrier. So if you've got LNG, it's probably only got an SG about 43, 47, something like that. And then we've got a high SG cargo. Well, it's going to go the other way. And obviously, with ballast, full ballast, it's going to go one way, and then you're damaging the cargo tank, and it's going to go another way. Now, loading patterns, that's... Yeah, sorry.
Did you take into account that if you damage a heavy cargo, the cargo will drain into the ballast tank? And
no, you lose it because you've already lost the ballast tank. In essence, it's not there.
Well, in your simulation, yes, but...
You can do real-time flooding calculations.
But it depends on where your cargo is, or where your damage is.
But it's vertical without limit over a distance. It's just like a big block going into the ship. So when you're doing salvage operations, that's totally different. You know where the penetration is. You can do mixed calculations. I'm sure you do those. This is a bit more simplistic than that. So loading patterns usually like that. Very rarely like this, but this is how an FPSO would be operated. And usually you don't see these in tanker books. You'd see that one. You'd see a very light draft. Product carriers, you might see this, because this could be quite a dense cargo. And you maybe, to get the longitudinal strength balanced out, you maybe only partially fill a tank like you would with a bulker. Bulker doesn't have full holds. Could have that tank. So when you think about all these different ways of doing it, it's actually your degree of dropout and everything that goes on is quite significant. And here you can see this is just a little fuel barge that operates in the southern England. And you can see there the different ranges of cargoes, which is different SGs. Also, loading patterns change, because obviously if we've got a variation in SG, if the SG goes cargo and condition both rise, the centre of gravity does rise. And this is one of the things that wasn't always accounted for, like on LPG tankers or chemical tankers, deck tanks. If you got the effect of that, your kg is going to go up. And sometimes these aren't in the standard conditions, because your normal conditions, there's only four. There's loaded departure, loaded arrival, ballast departure, ballast arrival. If you've got a complex ship to operate, there has to be more and more complex conditions. And just to show this is a combined critical kg curve, and this shows the difference here. The solid lines are when you have a bare boat, in essence, and this is where you've got 100% water ballast in the wings. And you can see the actual critical kg curve. This is your envelope of safety. So if you're below here, you're safe. If you're above there, you're unstable. And you can see how that changes. I've got the sum in the paper, and some of the differences are quite extreme. So we've got bottom damage there. Then we've got raking damage, which is totally different to bottom damage. So you've actually got three types of damage going on, side, bottom, and raking, that are giving totally different results. And this one just shows a set of GZ curves for the same damage on 14 different conditions, and just see how the GZ curves, how the angle sometimes it goes towards the damage, sometimes it goes away from the damage, just depending on what's going on.
So as long as you've been doing damage stability checks for these types of ships, have you been looking at all these conditions, or was it something that kind of has evolved in the way you've been
We wouldn't. No, I always did.
Okay.
We always tried to do that, but we were more FPSOs, so you've got more. You've got set sort of loading and offloading scenarios, of which you usually do 2 or 3 sets. So usually the OIM or the master can stay within. So you do in about 30 minute steps is what we used to do for offload anyway. So what's the point of having the critical kg an intact critical kg curve on a tanker? This mess of lines is actually combined critical of what would use to produce the envelope curve, which I'll show you in a second. So these are different trims, and this is draft across here, an allowable kg. Those lines there, the solid ones, are the intact lines. These lines here are all the different damages. So you can see no stretch of the imagination is intact dominant at all. However, as I've tried to show, the production of these is awfully complex, and this is what we've done in the past to do this. So the old British adage, red you're dead, here, you're stable in the white zone, and you can see here for different damages on different zones along the ship, because the ship has numbers as you go along, 1, 2, 3, 4, 5 towards the back, and different trims will have different lines. But for a tanker, you can end up with 75 of these, and it probably takes me as a naval architect 3 months to produce them. Lloyds hate them because they cannot verify them, because they've got to do as much work as I've got to do and don't have the time. But you can see how that changes. So this one is 100% water ballast and cargo. That one is for the transit conditions. Then we've got different ballast and cargo going on, and you can see them all massively different. So to produce curves, some curves are produced for tankers that are very condition specific. So we can see here, there's curves for this one and that one, and the curves are valid for only those degrees of loading, and the same for there. But as soon as you go deviate from those degrees of loading, it's invalid. This shows your intact curve here with a set of damage curves, assuming the dropout from there. So if I was proving a design to a client, this is a nice, easy way to show that your ship's safe from a point of view of people that write big checks, but not for the man who's operating the boat, because that's a defined loading condition. And again, there's another one. Really, the only way, therefore, to do that is to use an onboard loading instrument, an onboard computer. Now, obviously, back in the days when I started, how do you produce those critical kg curves? If you've got a passenger ship, you have one curve for one trim. That's a combined intact and damaged curve. You can see here you can't do this for tankers, so it was never done. So if you deviate from your loading condition, you couldn't be sure you were correct. So the only way to do that is to allow for loading computers. Now, a loading computer isn't just something that goes and interpolates off the kg curves. It actually does the calculations that a shipbuilder, a class society would do direct on a 3D model of the hull internal topology. And these have now come into force and are required for all tankers constructed before 16 that have to be fitted by basically the end of this year. So the issue's been solved through technology. However, there is some guidance have to be given to the verification and construction of these loading computers because they're different to the old loading computers. These are Type 3 loading computers. And this just shows from a chart that was produced by Andrew, by the UK MCA, a flow chart to when you need to use a loading computer. Now, it's in an earlier paper that we gave to Damage Stability 4 2 years ago. So if you want to go through this, I'll happily go through it with you later on, or if you want to have a look, it's in the paper. There has been, through the development of these regulations, input from different organisations, IMO and such like, but there was still a lot of questions coming about of using these Type 3 computers. And just as of the middle of last year, the MCA finally produced a guidance note for people to do these. That was done in conjunction with shipbuilders, class, people like that. So this is the just a quick skim through what 611M contains. It's an introduction, and the one thing it does do is brings everything under one cover. You don't have to go and look away at different things. Everything's captured under one cover. So this is nearly a one-step shop that you can get all your answers in of how to produce one of these. So, and there's 2 appendices to this, which go through into how to approve such things. And a lot of this was developed over, was it about 3 years, Andrew? You know, with industry, going back and forth with lots of questions. And I've got 2 of the questions highlighted in the paper. And pretty fundamental questions. This one, what if the approved damage stability information book, the trim book, does not comply with the stability instrument? So I can tell you now, I have done models of ships where I can't get the correlation with the original trim book. Now, whether that's because I can't get the lines planned, that's back this morning, because the computation methods have been differed, the final book might not actually be the final hull that was built, but that's the lines I've got. It's all happened. You've been there. You've done this. And people, you know, certain organisations I've worked on, it's got to be right. It was done by this programme. And I'm thinking, well, I've done it 25 years later. I think technology's moved on. And obviously that's an issue. You've really brought something up here. And really, you know, the answer to this is, well, as long as you're within tolerance, that's okay. Because if you're on board a ship and your loading computer goes down or you get a different answer, the reference document is your trim book. That always stands as the main reference document. So if your loading computer, when it's put on, doesn't agree, you've got an issue. And obviously, if it's an old ship and there is significant differences and they're found to be different, you maybe got to now produce a new trim book, or SIB as it's done there, to make sure the 2 actually do coincide. Another good one, and this is something that I used to sometimes do and not do, is intermediate damage. Everybody thinks about the final water line. Well, sometimes, but not normally, intermediate damage isn't dominant. It's usually final stage damage. And, well, yes, you could, but should it be analysed? Probably yes, is the answer. It does take longer, because if you've got one final stage of flooding, you've probably got 4, maybe 5, if you go up in 20% blocks. So you've just, you know, quadrupled your calculation time. So that's about me. Obviously, I've tried to show you what rules are there. That there's been issues with masters knowing what's out there, and that's because of the way that tankers are operated and what they are, and the complexities of getting that across to the master. However, the advancement, if you take anything in hardware and software, whatever Rodrigo said, it's either hardware or software. I don't know which one it is, but certainly the computer programmers seem to be use more and more of the available power. But calculations are significantly faster. And now that, as of 4 years ago, the introduction of loading instruments has come on. And I would just say that whatever the outcome of going through that matrix is that really UK Flag's position and my personal position is really it's got to be an onboard loading computer. It's not difficult, it's not hard. You just have to make sure the master knows how to do it. He isn't a naval architect, after all, but he is a highly qualified engineer. So that's the end of me. Thank you very much indeed.